Okay, so now I want to talk about the thing that I really want to talk about, which is so I've been doing this work kind of like this concept of the time traveling debugger for more than a year now.
Okay.
And I mostly I've just been freestyling. I would say I was inspired by a bunch of technologies like Redux is a big one, I think, and but also Python tutor, right? And and other than those inspirations that I had, mostly going off on my own without reviewing any of the literature of what other people have done, and only
Mhm.
recently have I tried to find other people, other prior art, other people doing a
Mhm.
similar thing, and there's something I told you about this. There's Replay IO, which is a solution for JavaScript. This is made by I had conversations with the CEO of this company. He's a previously a employee at Mozilla, and
Okay.
they actually start building the technology for this at Mozilla, and then
Okay.
it got spun off into this company. And then there's something called Oz code as well, which does a similar thing to what I'm doing for .NET, for like C sharp.
Okay.
More recently, I discovered something called RR, rrproject.org. So
Mhm.
RR is a basically a time traveling debugger for C and C++.
Uh-huh.
It only works for Linux currently. Um, and and what's really interesting is the way that it works. And what's also really impressive about it is so they developed this technology at Mozilla Research. And they specifically had the design goal of making it work for debugging the Firefox browser.
Okay.
And the Firefox browser is an extremely complex piece of software, as you can imagine. Like any production level browser, right, is a really complex piece of software, and
Okay.
they wanted to build something that they could use to debug Firefox.
Uh-huh.
So that's a very difficult task, I imagine. So far, the stuff I've been using to debug are very small programs,
Uh-huh.
relatively speaking. Um, and so in order to make that work, they they actually had to do a lot of extremely ingenious ingenious solutions. Like they some of them are really crazy hacks.
Okay.
But I want to explain the concept of how it works. And there's also like a YouTube video where one of the creators uh, talks about it, and there's also a paper that they released about
Mhm.
this technology. And I guess it's this is not the when I dug more into the literature on this, I realized that this is what they did here was there's already a lot of prior work before this. Like
Mhm.
they were using like there's a lot of work in the research community uh, on this, and the term they use is deterministic replay.
Okay.
So
Mhm.
if you search for deterministic replay, you'll be able to find a lot of the research literature on this prior work, and I want to talk about what that is. We're gonna start with Redux first because it has a lot of similarities to Redux actually. So in Redux, we have this situation where, well, you have your program. And the desire of Redux is to sort of encode your program as a reducer as much as possible, right? Because a reducer is a pure function, and pure functions are easier to deal with. And the reducer, I'm gonna try to. There's 2 inputs and 1 output. Okay, that's what the reducer does. The first input is the current state of the program, and the second input is some sort of action or event. I'll call it A for action. And then the output is a new state. I'll call it state prime, right? In sort of mathematical notation. So this is more or less what the Redux architecture is, and what you end up having is a timeline. I've drawn this many times, where you have state 1, state 2, state A1 goes in here, and that spits out a S2, and then A2 goes in, and then it goes to the reducer again, and spits out the S3, and then you build up the timeline this way. And in fact, yeah.
Is this a finite state machine?
Is this a finite?
Sure.
Is this a?
There only be like definite amount of the state that you can generate, and then which it depends on what is the event and the current state.
Usually, finite state machine, you draw it like this. But each of these bubbles is like an enum. Like if you have states A, B, C, then the state is represented as A or B or C. It's represented as an enum.
Right.
Usually that's how they do it in finite state machine. Maybe it doesn't have to be that way. Maybe you can have like state in terms of a variable value or stuff like that. But I don't know if that still counts as a finite state machine. In this case, our state could be any amount of information.
Okay. So the difference is we don't know what the states are. It's not presets of state.
Yeah,
because
the state could be any amount of information. Like any amount of there could be a like 10K of data, right? For example, or the data structures that have like very interesting linkage between each other.
Okay.
So anyway, so that's sort of the picture, and if I were to draw it in a simpler manner, it might look like this. Like so these are A's, and these are the S's. Maybe I start with a 0. How about that? And so the observation. So one of the sort of mind-blowing features of Redux is that, well, you can travel back in time if you follow this architecture, because there's 2 ways by which you can do that. One way is number 1 is you store the value of S0 and all actions, all A's. And if you store S0 and all the A's, then you can later on start with S0, replay all the A's through the exact same reducer that you have, and then you can generate all pass states that way. You can regenerate S1, S2, and so forth. The second way you can time travel is you just store all of the S's.
Okay. So is it like kind of like how Git works, like the first one?
Git works in the second way, actually. Yeah, Git stores all of the states. And
Okay.
but the predecessor of Git is SVN, and SVN does it the first way.
Okay.
Okay. So it's first of all, it's interesting that there are two ways to implement time travel, and also interesting that it's not clear that one way is clearly better than the other, given that we have different tools that use a different strategy out of those two. And in fact, I have implemented both of these. So so first I implemented the play language. The play language was based on number 2.
Right.
I had the end all of the state of the program, including the stack frame and the heap objects. All of that were sort of encoded inside of one gigantic data structure. And then whenever the program changed anything, I don't mutate that. I create a new version of the entire program state. So I use Git's approach for the play language, and then but for the Python one, I'm calling my Python time debugger, I call it PyRewind. For PyRewind, I'm using approach number 1, in that every action that any action I'm gonna define as any state mutation or the fact that a particular line in the program has been visited, has been reached. Those are actions. Any of those, I save those into the log file. And then the initial state, well, I don't explicitly store the initial state, but the initial state is just like the beginning of the program, right? So then I just run back all of those events to regenerate all the intermediate states of the program. And then now I can have a debugger that goes back in time, right? Okay, so I have tried both of these approaches myself. One of the biggest worries I have right now is that the performance it can easily be a problem if the program is doing too much, right? So that means I'm gonna have a very long list of actions, and and the time complexity of my thing that recreates the past states is gonna be determined by how many actions there are. So how does RR do this? RR takes this diagram. It's the same diagram, except that for RR, this is the outer box. Oh, one thing, by the way, one big limitation of Redux is that even though they have this very nice vision, I would say the ideal has not totally been achieved, because the time traveling capability, when you're using it to debug stuff, sort of it sort of only works for the thing that's enclosed inside of the reducer, like. But the problem is with Redux applications, there's actually a lot of code that's not in the reducer. And if there's bugs in that code, then the time traveling doesn't always help in debugging those problems, right? The problem is you haven't housed all of your code inside this sort of sandbox that it's able to capture. You're only capturing sort of this, what the reducer is doing. In other words,
write your code in a specific way to fit in the diagram.
The reason this came about is, we really like functional programming, right? So because and we can write a reducer as a pure function. The concept of reduce came out of functional programming. So basically, functional, like immutable functions or pure functions are easier to debug, and that's why we would like to have this. But the problem is that just, you cannot write all of your code as immutable functions. It's still not possible. So with RR, we draw the same diagram, except where we have the outer box. It was for Redux. It was your program. The outer box is the operating system, and your inner piece is your program. Okay, maybe I shouldn't draw it exactly the same way. So I'm gonna say, like, this is your program. And then we had the actions. The actions are the system calls. And if we're using a pure function in Redux, because a pure function is completely deterministic, as in given the same inputs, you will always have the same output, and that's why we can do this whole thing. We're in RR, it's the same concept, but we're saying the program is completely deterministic. As the system call is the way by which a program can communicate with the rest of the world. This is a two-way arrow. So the program makes system calls, and then it gets return value from system call. A system call is like, the API of the operating system, right? So in a sense, maybe a better way to draw this would be the program interacts with the operating system through the system calls. So if the program code is deterministic, then we can guarantee that if the same program ran and every time it made a system call, it received the exact same result, then it will do the exact same thing it did the first time. And if you think about it, there's this exact same picture that we have. Even though we have this state arrow in here, and now we don't have this state arrow, whenever state mutates, state mutation happens inside here. But if the way the program works is completely deterministic, then given the same inputs, the exact same state mutations should occur the second time.
So basically, the system call is the actions, and then we like the first row, like you have the in where the program starts, and then you have all the actions with the system call, and then that's how you create.
Yeah. You could still kind of think of it like this function here. Like you can still think of it like this reducer thing, except that we don't generate a new version of the state. We just go ahead and mutate it right inside. But if we can think about it as, if we can model it as the reducer, like whatever state it had, we're just gonna write it right back into it, plus whatever system call. If we can model it like this, whatever your current state is, you run it through this function, and then the output goes right back into the current state, and then it's the same as mutating that state. If we draw the picture this way, and this piece is deterministic or a pure function. This is a pure function. Or this is deterministic. Meaning if given the exact same input, it will always give the exact same output. Then this scheme will work. So what RR does is it runs the program while recording all of the results of the system calls.
Okay.
And then when it replays, it secretly intercepts all the places where your program is making system calls and replaces the results with the previously recorded versions of the values.
Okay, question.
Yeah.
So if the biggest difference that I saw between this schema and the one that's in the Pi one, and that took a long time. And because you have that, so that you can jump into like a random line of the flip, just recover that state. So how do you do it in the R? Or how do you say, okay, I want to go to the line, and then I want to go from there. I want to see that.
Yeah. Great question. Yeah, you were breaking up a little bit, but I made out what you were saying. Basically, you're saying, like with my Pi Rewind implementation, I have the full log and I have read it all back to generate every intermediate state. With their thing, they don't actually have all the intermediate states. The things they record are all the system calls, right? That's what they're recording. They're recording all the system calls, and they're not recording everything that happened inside your program, inside your building block here. They're not whereas my Pi Rewind, I actually do record every single thing that happened. Like this list got updated. I just added an item to this list. I record it. I mutated this dictionary. I record it. I changed the value of this variable. I record that in my Pi Rewind. They don't do that. Everything that happens inside this black box, they don't touch. They just touch things when the black box is communicating to the operating system. That's what they log. So the way they would have to implement traveling back in time, did RR choose scheme number 1 or scheme number 2?
The scheme number 1.
Yeah.
Right.
So RR chose scheme number 1. And the way scheme number 1 works is you start at state 0. And then you have to replay all of the actions leading up to that point, right? So what that means, if you want to rewind back to state number 2, you're going to have to start at state number 0, replay the first 2 actions. In their case, the actions are the system calls. So they're going to replay the first 2 system calls starting at state number 0. Now they could potentially choose to optimize it by, like, if the user has to jump around a lot in time, they could potentially choose to optimize it after rerunning these to get state number 2. They could store state number 2 in a cache, right?
Okay, gotcha.
They could do something like that, so they don't have to go back to the beginning all the time.
Gotcha. Yeah, that makes sense.
Yeah. So this is really interesting to me. I found that, like, the moment I search for deterministic replay, which is the term for this kind of technology, I found a lot of research articles, research papers on this topic. So I'm kind of wanting to do a deep dive on this. There's even crazier stuff where, well, I won't keep you too long, but I just want to share that stuff with you.
Cool. Talk to you later. Yeah, thanks for sharing. That's very interesting.
Yeah, you're welcome. Talk to you later. Bye-bye. Hey there, this is Toby coming to you from the future, as they say. I realized that in our conversation, we missed one thing when I was trying to answer Huiqi's question about with RR, how do you travel back in time? I did not give the complete answer, so I'll try to complete it now. So we did mention that in order to jump back in time to some state in history, you're gonna need to start at S0 and then replay the actions, which in the case of RR, those are the system calls. The question though is, in a debugger application, you actually need to be able to step to a particular line of code. However, that is not possible with simply representing a state, because remember, in RR, these are system calls. So if we replay the system calls, if we replay A1 and A2, both of which are system calls, and that gets us a new state S2, that only gives us the state of the program immediately after having completed a system call. What if what we want is to step into a point in time in the program's execution somewhere in between S1 and S2, right? Like I want S1.39. How do you do that with RR? And the answer to that question is we use the normal debugger that you would use, and in their case they use GDB. Okay, so if we, let me clear the screen. So if we want to pause at a state that's between two states, right? What we'll need to do is use GDB to set a breakpoint at that line location in that code, and GDB has facilities of doing that kind of stuff. The actual way to do it, I believe, you can either use a hardware breakpoint if your CPU has support for that, or GDB might actually modify your actual code in order to insert a breakpoint. In any case, we're going to ask GDB to basically insert a breakpoint into a line location somewhere in between state 1 and state 2. And then, so then after that happens, what we're going to do is basically replay these system calls. And after we replay system call 2, it's going to cause this chain of executions. We're going to hit this breakpoint, and that's going to cause the program to pause. And that's how we go back in time to any line that we choose. So yeah.